Welcome to the Vera Electrons for the presentation on AC fundamentals. Let's get started. We will start by covering the outline of our discussion. First, we'll discuss the AC terminology such as cycle, time period, frequency, amplitude, average value, RMS value, phase and phase difference, along with Phasor diagrams for sinusoidal quantities. Next, we'll examine AC circuits with individual components, resistance only, inductance only, and capacitance only. Following this, we will explore the concept of resonance in both RLC series and RLC parallel circuits. Finally, we will conclude with a detailed look at the transformer, covering its EMF equation and the voltage transformation ratio. AC and DC circuits. Let's first establish the difference between AC and DC circuits. AC circuits or alternating current circuits are defined by a flow of current that changes direction periodically. This is the electricity standard used in most homes and grids. In contrast, DC circuits or direct current circuits feature a current that flows in only one direction. AC electricity standards and DC electricity sources. Looking at AC electricity standards, the main supply voltage and frequency vary globally. For example, the UK main supply is typically around 230 volts with a 50 Hz frequency. The United States main supply, on the other hand, is about 120 volts at 60 Hz. DC electricity is supplied by sources like batteries, solar cells, DC power supplies, and switch mode power supplies or SMPS. Alternating current and key terms. An alternating current signal is also called a sinusoidal signal because its value varies like a sine or cosine function. It is crucial to understand the following terms for an alternating current: cycle, time period, frequency, amplitude or peak value, and peak to peak value, average value and RMS value, wavelength, phase and phase difference. Alternating wave shapes are primarily represented by their maximum amplitude and their frequency of alternations. Starting with AC terminology, a cycle refers to one complete wave which consists of a positive and a negative half cycle. The positive half cycle is when the current or voltage rises from 0 to its maximum positive value and returns to 0. The negative half cycle is when it goes from 0 to its maximum negative value and back to 0. The time period denoted by the symbol T and measured in seconds is the time taken for the alternating current or voltage to complete one full cycle. Frequency. Frequency, denoted by F and measured in Hertz, is simply the number of cycles completed by an alternating current per second. It has an inverse relationship with the time period where the frequency F is equal to 1 divided by the time period T. Peak value. The peak value is the maximum value reached by an alternating current or voltage during either the positive or negative half cycle. It is also known as the amplitude of the waveform. The peak to peak value, VPP, is the total height of the waveform measured from the maximum positive peak to the maximum negative peak. Average value. The average value of an alternating current or voltage is the average of all the instantaneous values during the positive half cycle and is calculated using the integral expression shown on the slide. The RMS or root mean square value is often called the effective value of an alternating current. It is defined as the steady direct current that would produce the same amount of heat in a conductor over a certain time interval as the alternating current would during the same time period. This is the most practical measure of AC power. The wavelength, denoted by the Greek letter lambda and measured in meters, is the distance traveled by the wave for one complete cycle. It can also be described as the distance between two consecutive peaks on the waveform. Phase and phase angle. Phase in an alternating current or voltage is the fraction of a cycle that has elapsed relative to a given zero reference point. The phase angle is the angle of rotation within a particular time period measured from that zero reference point. The phase difference is the difference in phases between two alternating currents or voltages of the same frequency. When two quantities are in phase, they have the same phase angle. This means their peaks and zero points match up at the same moment in time. Out of phase. When two waves are out of phase, they do not reach their peaks or zero points at the same time. The slide illustrates a scenario where wave A leads wave B by a 90-degree phase difference, meaning wave A reaches its maximum value 90 degrees earlier than wave B. Moving on to three-phase AC, this system uses three generator windings equally spaced around a circle, which produces three separate output voltages that are 120 degrees out of phase with each other. A key advantage of a three-phase system is a more efficient distribution of power. These three windings can be connected in the form of a Y or star connection. In a Y or star connection, all coils are joined at one neutral point, and the opposite ends are the output terminals A, B, and C. 120 volts is typically derived from a phase to neutral connection, while the voltage measured between any two phases is 208 volts. Alternatively, in a delta connection, any pair of terminals will produce a 240 volt output. AC circuits with resistance. Now we begin looking at AC circuits with individual loads. A circuit with an AC source is called an AC circuit. When a pure resistor is connected as a load, it is an AC circuit with resistance only. A pure resistive circuit offers the same opposition to current flow in both AC and DC systems. Crucially, in a purely resistive AC circuit, the voltage and current waves are perfectly in phase. Mathematically, the instantaneous voltage across the resistor is represented by Vmax sin omega t. The instantaneous current flowing in the resistor is IR Imax sin omega t. The impedance Z of the circuit is simply equal to the resistance R. Next is an AC circuit with inductance only. As the sinusoidal voltage rises, the change in current induces a magnetic field. This field generates a self-induced back EMF that opposes the change in current, following Lenz's law. The circuit consists of a pure inductance L connected across a sinusoidal voltage Vmax sin omega t. Phase relationship. Due to the back EMF generated by the inductor, the change in current is delayed compared to the voltage change. Therefore, in a purely inductive circuit, the current lags the voltage by a 90-degree phase angle. The instantaneous current flowing through the inductor is IR Imax sin omega t, 90 degree. This equation clearly shows the 90-degree phase lag. The impedance of the circuit is its inductive reactance XL, which is the factor opposing current flow in the AC circuit. In a purely inductive circuit, the current lags the voltage by 90 degrees. AC circuits with capacitance. Now let's examine an AC circuit with capacitance only. As the AC voltage continuously changes, the capacitor charges and discharges, storing energy in its electric field. It charges when the voltage increases and discharges when the voltage decreases. In a purely capacitive circuit, the capacitor quickly responds to the current, causing the voltage across it to build up gradually. This results in the current leads the voltage by a 90-degree phase angle. The impedance of the circuit is its capacitive reactance XL, which opposes the current flow. The key point here is that the current leads the voltage by 90 degrees, meaning the current reaches its maximum value before the voltage does. Resonance. Every object has a natural frequency at which it tends to vibrate when disturbed. Resonance occurs when the frequency of an external force matches the object's natural frequency. At resonance, the object will vibrate with a much larger amplitude. Resonance in RLC series circuit. In a series RLC circuit, the resistor, inductor and capacitor are connected in series. Current flows equally through all components. Let's look at the effect of frequency. As frequency increases, the inductive reactance XL increases and the capacitive reactance XL decreases. For instance, at infinite frequency, the inductor behaves like an open circuit and the capacitor behaves like a short circuit. Resonance occurs when the inductive reactance XL equals the capacitive reactance XL in magnitude. At this frequency, the reactances cancel each other out and the circuit's impedance becomes purely resistive. This is the minimum impedance the circuit can have, which in turn leads to the maximum current flowing through the circuit. This frequency is called the resonance frequency. Resonance in RLC parallel circuit. In a parallel RLC circuit, the RL and C components are connected across the same voltage source. Here, the current is divided among the components. As frequency increases, XL increases and X decreases. For example, at infinite frequency, the inductor acts as an open circuit drawing no current and the capacitor acts as a short circuit drawing maximum current. Parallel resonance also occurs when X equals XP. In this configuration, when the reactances cancel, the impedance becomes purely resistive and reaches its maximum value. The circuit's net reactive current becomes zero and as a result, the total current drawn from the source is minimum. We now shift our focus to the transformer. A transformer is a passive electrical device that transfers electrical energy from one circuit to another using the principle of electromagnetic induction. It works based on mutual induction between its primary and secondary windings, which are both wound on a common iron core. When an alternating current flows through the primary winding, it creates a continuously changing magnetic flux in the core, which then links to the secondary winding. According to Faraday's law, the changing magnetic flux induces an electromotive force or EMF in the secondary winding. The first type is a step-down transformer. In this type, the primary winding has more turns than the secondary winding, which causes it to reduce a high voltage to a lower voltage. Common uses include power distribution systems and mobile chargers. The second type is the step-up transformer. Here, the primary winding has fewer turns than the secondary winding, which causes it to increase a low voltage to a higher voltage. Step-up transformers are commonly used in inverters, X-ray machines, and for power transmission over long distances. The transformer EMF equation quantifies the voltage induced in each winding. The alternating magnetic flux induces EMFs E1 in the primary winding and E2 in the secondary winding. The equations for the RMS values of these induced EMFs are derived based on the number of turns N1 and N2 and the maximum magnetic flux. The voltage transformation ratio, often denoted as K, is the ratio of output voltage E2 to input voltage E1, and it is equal to the ratio of the number of turns in the secondary N2 to the primary N1. If N2 is greater than N1, the transformer is a step-up type, increasing the voltage. If N2 is less than N1, it is a step-down type, decreasing the voltage. Problem: let's look at a quick problem to apply this concept. A transformer with 1 zillion primary turns N1 and 400 secondary turns N2 is supplied from a 220 volt T1 AC supply. We can use the transformation ratio to calculate the secondary voltage E2 and the volts per turn. Applying the formula, the secondary voltage E2 is found to be 88 volts. Thank you for watching. If you found this video on AC fundamentals helpful, please like and subscribe to Veera Electrons for more engineering content.